Okay, hi folks. Welcome to the new session of algorithm and programming in C. And here today I am trying to discuss about complexity in algorithm. Previously we discussed about what is algorithm, right? Algorithm is procedure or a way or steps to solve the problems. Okay, algorithm is just a way. It's like a procedural way of solving the problems, like programming problems. And now we are trying to discuss about the complexity in the algorithm. That means what is the complexity of using the particular algorithm. Complexity means like what is the memory uses and what is the execution time that it takes, that the particular algorithm takes to execute uh, the, the program or solve the program or perform the actions, like perform the execution. So what is the complexity? So this we are going to discuss here. Okay, what is the complexity in the algorithm of any kind of algorithm? So how to find the complexity of the algorithm? So what is done in the complexity analysis of algorithm? This is the first question that you have to ask to yourself. That is, what is done in the complexity analysis in the algorithm? And we try to forecast the resources. Two main kind of resources are used in algorithm, in programming overall. Okay, so they are needed for the algorithm to execute. That means so whatever algorithm you design, you are going to need two kind of resources. There are memory resources and the time for the execution. So while analyzing the complexity, we suppose machine independent, right, and single processor and independent of the input data of a particular instance. So this complexity is mostly focusing mostly on independence of machine, whatever machine you are using, like whatever computer you are using to run the algorithm, or whatever processor you are using. Okay, Intel processor or AMD processor, any kind of processor, any kind of machine, or it is independent with any kind of machine. It is independent of the processor, and it is independent with the particular instance of problem. So whatever problem it be, alright. So the complexity of any algorithm depends on the size of the problem. So this is the concept that you guys have to understand. Is like it is going to depend on the size of the problem. Size means any kind of size. So any kind of size can occur, and the important conceptual thing that you guys have to understand is the complexity overall depends on the size of the problem. What is your size of the problem? Maybe the size of the problem you are trying to analyze is very big. For example, your computation must be very big. It's like for and that goes to that tends to infinity. That means the limit is very high. Okay, so during this concept, then the complexity should be analyzed. Okay, for smaller um, sizes, complexity do not play any kind of role, because for a small life the problem is just one. You have to just do one computation, and it doesn't matter, right? If you have like 10 problems, you have to just compute it 10 times, and the complexity doesn't matter at all, right? uh, Now, yeah, size of the files to sort. For example, you want to sort a file. Okay, so you want to sort a file. Now two things comes to play, that is memory occupation and the execution time. Right. And hereby I have classified the algorithm according to some certain complexity, and those are like you can see, those are uh, this complexity can be analyzed in many factors, and those classification I have noted here is like one is a constant. If a size of the problem you want to analyze is 1, that is a constant number, right? It is countable. So constant and countable, you exist, like 1 is constant. So the complexity of any algorithm that runs one execution is a constant. Whereas if a complexity like the second one is a log of n, that is logarithmic. That means if the execution time depends on log of n, right? So it's going to be log n. The complexity is going to be log n. Whereas for n size is n. Size of the problem is n, that is linear. Okay, if the size is n log n, that is linear n times logarithmic, that is linear arithmetic, both combined together. And n to the power 2, that is quadratic, n to the power 3, that is cubic, and to the power n, that is exponential. All right. So now worst case asymptotic analysis. So what is this worst case asymptotic analysis? For that, before you have to understand one thing, that is asymptotic. What do you mean by asymptotic? That means a limit that is going or tending towards the infinity. So for smaller n, as I have already noted before, for smaller n, the complexity is irrelevant. Okay, irrelevant. That is irrelevant. Okay, so what is irrelevant? Means like it is not needed. Okay, you can also say that this is a very complex word. Complexity is not needed, not occurred. So complexity is it doesn't matter. Okay, it does not. I mean complexity does not matter at all. All right. So for smaller n, if the smaller n is for constant size, for constant it's like we have to analyze the complexity that our execution time doesn't go to infinity. Otherwise, like it is not going to execute at all, and the algorithm is not useful at all. All right. So that's the concept here that you have to understand. Now we try to guess the upper bound. Actually, in asymptotic analysis, worst case asymptotic analysis of any algorithm, we have to try to guess the upper bound. Okay, for the time complexity, like that execution time for any algorithm on n data. Okay, in the worst possible case, that is done in a worst case asymptotic analysis. The worst case is most frequent. Actually, it occurs most frequently in any kind of algorithm that you design. Okay, so and also this must be taken into consideration while designing algorithm, because if a worst case occurs in an algorithm, then the algorithm is not useful at all, and we have to be careful to use such kind of algorithm, okay, for implementing to solve our problem. Okay, so why we do complexity analysis of algorithm then? As I have already noted, the key concept for doing the complexity analysis of any algorithm is like we can easily find the efficiency of the algorithm, any algorithm, and the efficiency that it performs, okay, will be easily analyzed by doing the complexity analysis, which will help us to choose the better algorithm for the problems, for any kind of problems that we use any kind of algorithm to solve any kind of problems. So it helps, the complexity analysis helps us to choose the particular algorithm, and it helps to improve the performance, okay, of solving the problems, right? So now complexity analysis of linear search. Okay, linear search, as I have in my previous algorithm session, I tried to give you some concept about linear search. So how is a linear search, what we are doing in linear search, and how linearly we search the key element. And while analyzing the linear search, what we find is the execution time grows linearly with n. N means the size of the problem. So in linear search, as you guys know that we are looping it linearly, right? So looping it n times. So looping it n times means the size of the problem is just n. Okay, so because as you guys, if you guys remember, there is a for loop, and we are looping it n times, right? From index is 1 equals to 1 to n. We are looping it. So also, as you know that the complexity depends, it's or directly proportional with the size of the problem. So also you can say that directly that the execution time goes linear with time. So complexity of a linear search is linear. Okay, so because we are iterating and checking the each element of the. So all right, so this was the one particular example how do we do linear like complexity analysis of linear search. Now complexity analysis of the binary search. So how is it done? Okay, at first iteration we examine n times. So here it is said like, okay, whenever, okay, now I will try to give you a key concept. Okay, the key concept about how do you analyze complexity of any algorithm. Previously you analyzed the complexity of a linear search, and you found out that the size of the problem was n, and from this basis, as you know that the complexity depends on the size of the problem, or that means like complexity is directly proportional to the size of the problem. So you can directly say that complexity of linear search is linear. Now for binary search, okay, you guys have to understand one thing is like whenever, okay, so this is the algorithm that is a binary search. Now I want to do the complexity analysis. So what do I do? First step is I try to find the size of the problem. Okay, so what is the size of the problem that is the binary search is trying to execute? So the first thing I go to the to see the algorithm, and when I see, as you guys also remember that if you go and check out in binary search, that is like the iteration, there is a external loop and the internal loop. Alright, so there is like a external loop and the internal loop. So for external loop, there is external loop, the iteration is like n times. Okay, so the first iteration we examine n times because there is a external loop, that is a for loop, and also internally there is a we have a second second loop that we examine n by 2 times. So what it is done binary search is like we have to divide the array, the input array into 2. Okay, so we divide it 2 times, then we check the middle element. So if the middle element is not equals to the key element, then we try to again like divide the array into 2. That means we are trying to see the left side of the array, and if the key element is less than the middle element, or if the key element is greater than the middle element, you are going to check the right side of the divided array, right? So similarly you try to check it iteratively. That means recursively you try to check overall elements, right? Again you divide, then again you divide the array into 2, that is left and right portion of the array, and if the key element is even less than the middle element, then similarly you go to the left, or similarly you go to the right. Alright, and from that concept I come to notice that at first iteration we do n times, and now in the second iteration we do it n by 2 times. That means the array is divided right now. So the problem is half. Now problem is divided to half. Okay, so each time the problem is divided to half. That means now similarly for ith iteration we examine n by 2 times I, 2 times I times, okay, 2 to the power I times. So similarly now we try to solve the equation, that is n by 2 to the power I equals to 1, because you know that when the array element reaches to 1, then when the array element reaches to 1, then the iteration must stop. That means the iteration must stop, and that means the algorithm executes or terminates, right? So we get I. So overall, by like you guys, if you solve the problems mathematically, you solve for I and you get the value of I is log of n, and in base 2. Okay, so log of base 2 to the power n, because this is 2 to the power I. Alright, so you get the value I is. So from this concept we say that the complexity or the time execution time grows linear logarithmically with n, that is log of n. The complexity of binary search is log of n. And now similarly we try to do the analysis of insertion sort, complexity analysis of the insertion sort, and what we found out here is like two things is to go and check out the algorithm of insertion sort. As I have noted this, I have clearly described insertion sort in my previous session, right, in algorithm, in session named algorithm. Now, yeah, if you check out from there, you will see that there are two loops, inner loop and outer loop. And for outer loop, you have to execute n minus 1 execution. That means the size of size of the problem is n minus 1 times. Whereas for the inner loop, in the worst case, the iteration will be also n minus 1 times. Okay, so here like outer loop will be maybe outer loop will be, yeah, so it depends on like what happens is like n minus outer loop n minus 1 times, and for inner loop n minus 2 times. So it depends. Okay, and no, actually what happens is like for outer loop it's n times n execution, and for inner loop it's like in worst case can occur I execution in the ith iteration. So for you can see also like this, like inner loop, and you will execute n minus 1 times by 2 divided by 2. That means divided by 2. So worst case, we can occur I execution in ith iteration, because only in the worst case you have to execute n minus 1 by 2 times. So overall, when you combine this both concept, that is n times into n minus 1 by 2 times, what you get is like your complexity becomes n times n minus 1 by 2. So overall, you will get a form like n square. Okay, so that is quadratic, right? So now complexity grows quadratically with n. So here is also said the best possible case, the inner loop one execution, so execute only one execution, so Tn grows linearly with n. Okay, so best possible case like only one execution can occur. So similarly you can so find that in the best possible case that the execution like complexity and complexity of this insertion sort will be 1, that means linear. That means the inner loop will be just one execution. So 1 times the n execution, the outer loop will result to the linear. Okay, now we have asymptotic notation. So we have 3 asymptotic notation. Okay, for information that there are 3 asymptotic notation. Okay, so and these notations are for asymptotic and notations that are for larger inputs, that is if the size of the problem is large. Okay, if the complexity analysis of the size of the problem is very large, then you have to use the asymptotic analysis, right? For that there are 3 kinds of asymptotic notations, and those are omega, big O, and theta. So which gives only the asymptotic information that is to be noted. And now for big O gives the upper bound, whereas big omega gives the lower bound, and big theta gives both the upper bound and the lower bound. That's why big theta is much more better, okay, than big O or big omega. So now this notation is not related to the best, worst or average case analysis of algorithm. Each one can be applied to each analysis. So each one of the algorithm can be applied to any kind of algorithm analysis. So whatever, it depends on yourself. Alright. So now for the example, I present here that is a merge search, and merge search is both big O of n log n and theta of n log n, but it can also be big O of n square, that is a quadratic. The complexity is quadratic, or since n to the power whole square is asymptotically bigger than it. However, it is not theta of n to the power whole square, that is theta of quadratic. I mean, the complexity is not quadratic here, because since algorithm is not omega, that means to be theta it must be both big O and big omega, because theta gives both. Okay. And now now we have one important concept, that is like connectivity. So connectivity is to find the connection between two or three objects. Okay, so connection means like are those two objects connected or not? Okay, so here I present you three kind of connectivity, that is like one is here, one is 0, and the other one is like there are three groups. Okay, so 0, 1, 4, 5. 1, 4, 5 is in one group, whereas 0 was in one group, 1, 4, 5 was in the second group, and the third group was 2, 3, 6, 7. Alright, so there are three connected components. So these all three groups are connected. And now is the path connected? Okay, the path connecting the two objects. Is there a path connecting these two objects? So are there any two objects that are connected? This means. So this is the this is the theory behind the concept behind the connectivity. So you have to find the path that are connecting these two objects. Alright. So are there any two objects, 1 or 5, in the same component? So I present here you three components, right? So you need to find, are there any two objects, 1 or 5, they are in the same component? And how can you solve this algorithmically? So how can you find algorithm to find or solve those kind of connectivity problems? And this connectivity is mostly used in wiring or many it has many usefulness. Okay, like it is mostly used also in the graph concept, in networking. Okay, so this connectivity is mostly used in networking. And now we have find. So in which component is object 5? The concept behind find and union is like, for finds like which component is object 5. In which component is object 5? 5 is in a component, second component, right? Connected component. Now union is like replace the component containing object 0 and 1 with their union. So like, for example, you want to make these two components as one component, and in this for this concept, like union is used. Alright, 0 and the first component and the second component can be just merged together by using this algorithm of union. And now hereby I present you these two concepts very quickly, and also here this is called quick find and quick union. And for quick find, you represent set as of connected pairs with array ID. And here I present you also the algorithm here, and it's like C algorithm here. Okay, and the basic concept of quick find is to find like, are they pair connected or not? Okay, so the algorithm goes in this concept. Now, so let's check out like what the algorithm says. We define the size is like 10,000. Inside the main function, we define all those variables, declare all the variables, define all the variables, then you loop it n times, that is the number of size times, then the id is assigned to I, that's the index, and you print out it says that you put here P and Q. And now you scan for two numbers. Okay, among all those numbers you scan for two numbers. Okay, and those two numbers are scanned by the user as a user input, and then you check conditionally, you check that the ID of the scanned numbers and the ID of the first scan numbers and the second scan numbers, are they connected or not? You check it. So conditionally, if you equate them, if they are equal, then you can directly see that those are connected. So otherwise if they are not connected, then what happens is like you loop it, there is an inner loop, you again loop it n times and you start checking for the connectivity. And then similarly you can say that here, like you have seen here that the id is initialized to the t, that is the id of p. Then id of I is tries to check if id of q are equated or not, because here previously it was not equal, right? Id of p is not was equal, like else id of p is not equal to id of q, then the pairs were not connected, and previously pairs were not yet connected, and now we start to connect it, okay, by using this inner loop. And now recursively it also tries to input another those pairs, okay, input pairs, and similarly you use this quick find to find the simple simple if the pairs are connected or not. Now here is another algorithm, that is a quick union, and in this union the purpose of this algorithm is also to find if the pairs are connected or not, but the basis of algorithm is different. Okay, so what's the basis of quick union? It's like we are trying to, previously we were trying to just to find, okay, and now we are just trying to find it as a union. Alright, because for union you try to replace the component as a union, as a whole, then you try to find for the connected component. For find, it was just finding, okay, the component if they are connected or not, right? So now for this one, the algorithm also says like it's going to do the outer loop, that is it loops for n times, and you start inputting the pair, and you scan the pairs. And now here are two important concepts that you have to understand, that is this two for loop. And what is the purpose of this for loop? Is like it is just setting I and j, that is I and j are set to p and q respectively. And what happens to the second part is like I is not equals to id of I, and I is equal to id of I, and z is not equals to id of j, and z is equal to id of j. And I and j will be 0 itself, and the purpose was just to set I and j here, that is setting to p and q itself. Set the, and also you have to set, the purpose is to set for all the id to something less than n, okay. And now respectively, okay, so if the I and j, that is p and q, those numbers, if they are equal, then you can directly say that the pairs are already connected. Otherwise if they are not equal, then you try to make the connection, that is the id of I, okay, is equated with j, that is assigned to j. And now here where you can say that previously the pairs were not connected, and now the pairs are made connected. Alright, so recursively it also input for those another pair of numbers and pairs, and then you try to solve the problem of connectivity. So this was all about complexity and some concept about connectivity. Now yeah, that was it about the complexity in algorithm. So thanks for listening guys, and hope to come back with some other sessions with some other new brand topics, and keep on tuning and don't